When you put a lithium salt into a Bunsen flame, it gives off red light. Now, red light is just a form of electromagnetic radiation. However, if I take the lithium out and put a copper salt in, it gives off this bluey green light, which is another form of electromagnetic radiation, but of course of a different wavelength. So in this lecture, what we're trying to understand is why these substances emit electromagnetic radiation when you put them into a Bunsen flame. The learning outcomes for this lecture are that you should be able to explain how the emission lines in an emission spectra are produced, how atomic emission spectrum is used to provide evidence of energy levels in atoms, and you should be able to use a data book to find out the wavelengths of various spectral lines. The phenomena of flame colours is really just part of what we call atomic emission spectra. And in order to explain atomic emission spectra, it's easier to try and explain it using the hydrogen atom, as that is the simplest atom. So here's our hydrogen atom. The nucleus is a tiny little dot in the middle here that you can't see. This is the first energy level, second, third, fourth. Now, hydrogen only has one electron, and that, let's put it in the first energy level where you'd normally find it. Now, in atomic emission spectra, the first stage is that electrons can, if given enough energy, be moved from a lower energy level to a higher energy level. Now, there's two different ways we give them enough energy. In the flame test, it's the heat from the Bunsen burner which provides the energy. Another way it's commonly done is by passing electricity through a vapour of the atom. Okay, so no matter what way you are providing the energy, if you provide enough energy, this electron can be raised from the first energy level to a higher energy level, let's say the second one. Now, the electron is not very happy at this high energy level. It's kind of unstable. It's almost like a ball at the top of a hill, and it's very easily going to roll down the hill. So, similar thing happens with the electron. It's going to eventually fall back down to the first energy level. It loses energy as it does this, and that energy gets emitted in the form of electromagnetic radiation. The wavelength of the electromagnetic radiation will depend on that energy gap. Remember that E equals LHC over 1000 lambda. So the bigger the energy gap, the smaller the wavelength. And if the wavelength of the radiation just happens to be in the visible region of the electromagnetic spectrum, we will see a colour associated with that transition. Now, even with hydrogen, it can get a bit more complicated, because it says we move the electron from a lower energy level to a high energy level. So when we excite this electron, it won't always just go into the second energy level, it might go up to the third energy level. And if it's in the third energy level, obviously it can fall back down to the ground state in the first energy level, giving out higher energy radiation. Or sometimes it will fall back in two stages. Initially it will fall back to the second energy level, give out that energy as electromagnetic radiation, then it will fall back down to the first energy level and giving that out. So from that transition you could get three different wavelengths of electromagnetic radiation given off: the blue one and the two different red ones. And it gets more complicated if you've excited the electron up into the fourth energy level, you can get loads of different transitions. So even for a simple atom like hydrogen, if you put it into a flame, there will be loads of different types of electromagnetic radiation being given off. However, that does explain the basic principle of atomic emission spectra. So electrons are moved from a lower energy level to a higher energy level by giving it heat or electricity. And then when the electron drops back down, it will emit energy corresponding to the energy difference between the two energy levels. Okay, here's a picture of all the different wavelengths of electromagnetic radiation that have been given off for the simple hydrogen atom. And they're split up into different series. So this is the first energy level, second, third, fourth, fifth, sixth, seventh. Okay. And here we've got all the different wavelengths of radiation emitted by electrons falling from the second energy level back to the first, from the third back to the first, fourth back to the first, etc. The energy gap between these electron energy levels is quite large, so this tends to give off light of a short wavelength, which means it's in the ultraviolet region of the spectra. So we don't, with our eyes, we don't see this. And that's called the Lyman series. Then we've got the Balmer series, then the Paschen series. In the Paschen series, it's all the energy transitions falling down to the third energy level. They tend to be quite small, the energy gaps. So they give off radiation of a long wavelength, which tends to be infrared region. So again, we don't see them. What we do see is the Balmer series, which are the electron transitions of the electron falling back down into the second energy level, and they just happen to have a wavelength in the visible region, so that tend to be the ones that we actually see. One other thing that's just worth pointing out at this stage is the highest energy line that can be detected, no, not seen, because the highest energy will be in the ultraviolet region probably. So the highest energy line, or the lowest wavelength, will correspond to the ionization energy of that atom. So let me explain. So okay, let's just stick with hydrogen. That's the first energy level, and this is not the second energy level, maybe the 8th or 9th. Okay. When we excite the electron, okay, up to this energy level, okay, it's still just close enough to the nucleus to be attracted by the nucleus, so it's still trapped within the atom. So you'll get a really big high energy electromagnetic radiation when that falls back down. Okay. However, if you go beyond this distance, the electron is no longer attracted by the nucleus, and so it escapes from the atom. In other words, the atom's been ionized. So the energy gap from the ground state to the furthest away electron energy level will correspond to the ionization energy. Any energy slightly greater than that value, the electron will be lost from the atom. Okay. Let's have a look at this picture. This is showing the atomic emission spectra of hydrogen. So we pass electricity through a tube containing hydrogen, and it gives out pink light. Okay. Pink light is passed through a slit just to turn it into a nice narrow beam, and then if we pass it through a prism, the prism splits the light up into all its different wavelengths. just like passing white light through a prism produces a rainbow. So if we pass the pink light through the prism, it splits it up into all the different wavelengths. And there's 4 different wavelengths of light given off by hydrogen. So 4 wavelengths that are in the visible spectra. There's other wavelengths that are ultraviolet and infrared. So the longest wavelength, lowest energy, gives us a line of red light at about 656 nanometers. We have a transition which gives us some blue light at 486, and 2 further transitions at higher energies, and which are also more sort of like purpley violet. Okay. So in the visible region, the atomic spectra, emission spectra of hydrogen looks like this. You get 4 different wavelengths of light given off, corresponding to 4 different transitions between the electron energy levels within the atom. Now, this information is given in your data booklet. So on page 15 of the data booklet, you get 3 tables giving the wavelengths of some of the light given off by different atoms. So for example, on the first table on page 15 of your data booklet, it lists all the wavelengths of light emitted by hydrogen. So 656, colour red, 486, bluey green, 410, 397, 434 and 410, sort of bluey violet. And it also lists 2 other wavelengths which are in the ultraviolet region, and so not in this picture, it's just showing the visible region. Also gives you the same information for what wavelengths you would see if it was helium that was being analysed. And in the second table in that page 15 of the data booklet, gives you the wavelengths of light that would be emitted if you used these metals, cadmium, mercury and sodium. And in the third table in the data booklet, it gives you the wavelength of the most prominent spectral line in flame tests. So it's not saying that in barium you only get light of 554 nanometers given out. There may be several lines given out, but this one is the dominant line, and so gives rise to the colour green that we'd see if we did the flame test with barium. So if we look back to where we started and we did our flame test with lithium, we see a red, or let's say a crimson flame corresponding to electromagnetic radiation of a wavelength of 671 nanometers. So let's say that's so corresponding to an electron dropping from a higher energy level to a lower energy level, not necessarily ground state, and the radiation given off has a wavelength corresponding to 671 nanometers. Whereas if it was copper that we did a flame test with, we get light of a wavelength of 522 nanometers. A shorter wavelength, which means that the energy is greater. The electron is dropping further distance in the copper than it was in the lithium, and so we get a shorter wavelength because it's higher energy radiation. So atomic emission spectra arises from the de-excitation of an electron from a higher energy level to a lower energy level. And by measuring the wavelength of that light, we can work out the energy gap between those 2 atomic energy levels and get lots of information about the structure of the atom from the emission spectra.